C++17's useful features for embedded systems. YUINT8_TB equals 0B1111 feet 1111. I would rather have UINT8_TB equals binary 1111_1111. This thing is hard to get right on some non-US keyboards. And yes, I've the same problem with Rust. Not really sure they are that useful for embedded systems. I think the most useful thing is in 20, and that is coroutines. For bare metal embedded systems this simplifies a lot of things, but isn't super common on embedded toolchains yet. I've heard coroutines in C++20 were dead on arrival, especially on embedded, because it may liberally do heap allocations to store locals and there's no way to control this. Typical library implementations I've seen for lightweight coroutines fibers seem to set the stack size for each coroutine as fixed. Isn't polymorphic memory allocator the most significant recent C++ addition for embedded systems that allows preventing runtime memory allocation after the init phase and thus allows conformity to MISRA and other guidelines for critical SW development, especially when using stdlib? Not a C++ developer, but Notice card is gross in my opinion. I've seen codebases littered with it for no good reason. Why should you care if the caller uses the return value or not? Everyone is mentioning error codes, but I think a better use is when the function returns some allocated memory, where ignoring the return value would be a bug. I'm not convinced Notice card is very useful, however. WRT hardware_destructive_interference_size. What happens if you compile for x86 which is then run on a machine, Rosetta, that has a 2x bigger cacheline internally? x86, generalized, and ISA doesn't have an inherent cacheline size. A given implementation of that ISA does. STD. Hardware_destructive_interference_size and friends are compile time constants, and are defined based not just on the target ISA, but the target implementation. See March and CPU for GCC and Clang. It does sorta bring up the general question of why this is a compile time and not runtime constant. I doubt x86 will double its cache line size anytime soon, but if it did, and people are running binaries with cache padding at 64 bytes, expected behavior is going to differ. Not in a way that's going to make anybody lose their minds, mind you, but this kind of micro-optimization will just cease to be effective. Edit. Naturally I understand that compile makes sense for e.g. statically sizing array sizes etc. Hey Rust, check it out. Compile time evaluation without macros, isn't that neat? So much of modern C++ is trying to get around just using the preprocessor. The preprocessor is such a botch, charitably, state-of-the-art 1975. As Stroustrup said to me once in a discussion on the topic, once an ecological niche has been colonized it's almost impossible to clean up, so you have to work around it. And for good reason? C++ should finish the job and deprecate the preprocessor. Modules get rid of includes and includes guards. Unfortunately the preprocessor is still needed for stringification and other symbol manipulation. C++ 26, 2126 of course, will introduce enough reflection to finally get rid of the preprocessor. I added enough to D that it didn't need a preprocessor, yet could do all those things. If constexpr is such a disaster, they were so close to getting it right, not introducing a scope, but they missed. Similarly constexpr itself is also genuinely ridiculous. I have said this on Hacker News before, it's such a stupid idea to require an annotation everywhere you want to evaluate things at compile time. Practically everything will inevitably be evaluatable at compile time, and you need the implementation anyway, so just let it fail rather than ask for permission everywhere. Having the keyword for variables and constants is fine, i.e. top-down and bottom-up constraints need to be dictated, but you shouldn't need to write constexpr more than that. It's such a stupid idea to require an annotation everywhere you want to evaluate things at compile time. Practically everything will inevitably be evaluatable at compile time, and making constexpr-ness an explicit contract makes sense to me. If it's not that it can be an unexpected property, and can break at any change of implementation. Yes, requiring a function being marked requires that the implementer do it, but it also means they have considered this use case and made it officially part of the API. It's not a trivial promise to make, and you need the implementation anyway, so just let it fail rather than ask for permission everywhere. Let it fail, is the issue. If it's implicit, a user can assume this is working by design, then find their program stops compiling on the next release, not because the maintainer willfully broke the API, but because they changed an implementation detail of the function, and context PRness is not something they considered, or assumed correct, in the first place. Maybe the language should work the other way around and everything should be context PR by default and functions should opt out of context PRness, but that's 40 years too late for C++. And I can't think of any language which does that. And frankly, it feels like the wrong default for the reasons above. Except context PR isn't a guarantee. Compilers can choose to silently evaluate context PR things at runtime. And I have ran into this before. A compiler with a recursion limit causing it to bail on context PR and just emit the code. So context PR isn't a guarantee of it being evaluated at compile time, and non-context PR isn't a guarantee of it being evaluated at runtime. Cool, huh? Context PR isn't a guarantee of it being evaluated at compile time. Context PR is a guarantee that you can use the thing in a context PR context, and this is where the evaluated at compile time guarantee can come from. Template auto-func. Here some compilers can still choose to evaluate X at runtime, and very likely all of them if no optimizations are enabled. Context PR int X equals F. But here it becomes mandatory for this use of X to be evaluated at compile time, since the number is literally going to be part of the compiled binary as part of the function name mangling return std, integral underscore constant. Is such a mangling mandated by the standard? Mangling is mentioned in the standard. In this case though, the underlying reason is that it's part of the type, system, not because of the mangle specifically. Mangling is mentioned in the standard. Forgive me, but can you be clearer than mentioned? Is the mangling required to contain template parameters for return types? In this case though, the underlying reason is that it's part of the type, system, not because of the mangle specifically. I'm not sure. The compiler knows it will always be the same type. So under many uses of this function I could easily imagine a compiler that doesn't actually fill in value until runtime. It's not a trivial promise to make. It's actually very trivial. 99% of code I write can be run at compile time. Maintainer willfully broke the API. Did they break the API or did they change the semantics? The API is tittle-tattle. The point is that you cannot run it at compile time anymore. E.g. accidentally introduced a opaque new dependency by accident? Oops. And I can't think of any language which does that. Being able to opt out is not what you want, but D allows everything to at least attempt to be run at compile time. This has been very profitable. Context PR is great. I can finally do most of the compile time computation that previously required template metaprogramming, and it's much more readable by comparison. C++17 makes it much more ergonomic to use 2 over C++11. I can't wait for us to finally upgrade our toolchain to take advantage of C++20. If you're in embedded and you're not pushing everything you can into context PR, you're missing out on correctness and code size benefits. Doing stuff at compile time is good. Although the compiler can do 99% of it anyway, it's nice to have guarantees. C++ just got it wrong. It could certainly be better. But in a world where my options are C, C++, or assembly, I pick C++ every day. I do keep hoping for something else to get big enough we can use it, because C++ sucks, but is still better than the alternatives we can use. Disaster? Just because it introduces a scope? Please elaborate. A scope is the right thing to do. Every other, introduce a scope. So if this wouldn't have been consistent with the normal, if, that would have been extra confusing. Maybe you'd like to do something like template struct ABC, int X, int Y. If context PR is underscore 3D, int Z. But yeah, that's not what if context PR does. I wish context PR actually asked the compiler to evaluate an expression at compile time and not just a statement. In D, every part of the grammar that is a constant expression must be compiled at compile time. For example, void test, int square, int Y, return Y asterisk Y, int X equals square, 3, evaluate at square at runtime and Y equals square, 3, evaluate at square compile time. Although, when the optimizer gets through inlining square, etc., it will wind up at compile time anyway. I would absolutely hate context PR to be implicit and left to be decided by compiler. What if it was always allowed to do compile time, but you could add a keyword to assert it did, like force inline? That way you get benefits by default. Whereas right now it's not allowed to. I'm sure other languages would have more than 17 useful features. The whole discussion about context PR, even though a useful feature, is one example, out of many, of what a F-up language C++ has become. It's astonishing how many people have to say, I don't like the language but there's no good alternative for the context we are working in. Especially with embedded applications, the issue is lack of tooling and sluggish vendors. For them, even C++ is too new, in some cases, to properly support. Rust is making good progress despite these issues, but it's still a pain to use in anything but the most common systems. As soon as you're using socks that have an FPGA part, for example, you're forced to use proprietary vendor tools, and good luck getting Rust to work with those in the next few decades. TBH Rust in the deep embedded space. Like MCUs, not MPUs. When I looked at it a bit ago, it was fairly dubious how much intense effort would be required to trim fat to get reasonable binary sizes keep the fat under control. I'm used to doing much of this with C++, but it seemed way easier to end up with a bloated binary in Rust starting a job in a week, which is embedded Rust. But more on the Linux on SOC side. We'll see it goes. Rust. The alternative is Rust.